So in this week's lesson, we'll talk about some exponential growth, which includes the laws of exponents, and then getting into some geometric patterns. So if we consider the expression 2 times x to the 4, that of course equals 2 times x 4 times. And what we have here is that 2 is called the coefficient, x is the base, 4 is the exponent, and 2 to the 4 is the actual power. And so from this simple idea, we can get the laws of exponents. There are 3 of them. The first one is multiplying powers of the same base. What we can do here is we can take a look at a to the 5 times a to the 2, and that equals a times itself 5 times, and then a times itself 7 times. Sometimes this is pronounced but actually what we have here mathematically is a to the 7. And so from this simple idea, we can see that when we are multiplying powers of the same base, and the base here was a, we keep the base and then add the exponents. And I think it's really important that you recognize that we need to have the same base and that we keep the base and add the exponents. And then, of course, if we have a scenario when we're dividing powers of the same base, like this, I have b to the 7 divided by b cubed. I can see that these b's will divide out. They will divide to equal 1. And what I'm left with here is b to the 4. And so again, from this simple demonstration, we can see that when we're dividing powers of the same base, we keep the base and subtract the exponents. Don't forget to keep the base. And the last one here is when we have a power of a power. So if I have w cubed squared, that's w times w squared, which would mean that the 3 w's are multiplied together by themselves. And then that would be w to the 6. So we have a power of a power, we keep the base, and we multiply the exponents. And so from this we can do some examples here. I suggest that you pause the recording and pause the video here and try yourself. I'll go over them in a few moments. So here are the answers. What we have here in the first one is a simple multiplying powers of the same base, so I keep the base and I'm going to add those exponents to give me the 13. Question B, I have some coefficients. I'm simply multiplying those together. That's where I get the 40. And then I have the powers, or multiplying powers of the same base. So I keep the base and add those exponents. Here I have coefficients as well in question C. 15 divided by 3 is always going to be 5. And then I'm dividing powers of the same base, and I'll keep the base and subtract those exponents. In question D, I have the base of 2, and so I have 2 to the 1 here on the bottom, in the denominator. Here I have 2 to the 3 times 2 to the 9. That's going to give me 2 to the 12. Oops, that's 12 to the 12. I don't know if I can erase that, so just pretend that that's not there. 2 to the 12 divided by 2 to the 1. Now I'm going to keep the base and I subtract those exponents, so it's 2 to the 11. In question E, again I have a power of a power here, but I also have the division of powers of the same base. And so that's going to be s squared, and then t cubed divided by t is t squared, and all of this is raised to the power of 4. So now I have powers of powers, and that's what I'm going to get. So I keep the base and multiply those exponents, and that's where I get s to the 8 times t to the 8. And there's nothing else I can do there really, because there's not a common base. It's equivalent to write that as st to the 8, but not needed. And question F, this looks complicated, but I have the base of 2, so I'm going to start there. I recognize the power of power, so I'm going to keep the base and multiply those exponents. That's 2 to the 6, 2 to the 5. Down here I have 2 to the 4. Keep the base, the power of power, and multiply those exponents. I get 4 again. So now I'm going to remember that, although it's not necessary here, but I'm going to still remember that there's implied brackets in a fraction. So I'll simplify the numerator here where I'm multiplying power to the same base, so I keep the base and add those exponents. And down here I do the same thing, keep the base and add those exponents. And now I have the division of powers with the same base, so I keep the base and subtract the exponents. Now, we're going to take these laws of exponents and apply them to a new concept, which will kind of destroy the model that we have here of what an exponent means. We started with something like w squared means you take the base and multiply it by itself, the number of times the exponent indicates. And so what we have here would be w times w. But if we keep the laws of exponents in mind, then this changes things. So, for instance, what does 2 to the 3 divided by 2 to the 3 equal? Well, we see that 2 to the 3 is just 8, and 8 divided by itself is always 1. So the answer here has to be 1. But of course, we could apply the laws of exponents here. When we're dividing power to the same base, we keep the base and subtract the exponents. And what we would get there is 2 to the 3 divided by 2 to the 3 would be 0. Or sorry, 2 to the 0. Keep the base and subtract those exponents. So what we see here is when we do this question out twice, different ways, we get different looking answers. But what that means is that those answers have to be the same. And so 2 to the 0 has to equal 1. And in fact, it didn't matter if this was a 2. We could have chosen the base to be b. b to the 3 divided by b to the 3. That's still b to the 0, but we also know it's 1. And so anything to the 0 equals 1. Now we can continue with an example here where we have 3 squared divided by 3 to the 3. And so we know what 3 squared is. That's 9. And we know what 3 to the 3 is. That's going to be 3 times 3 times 3, which is 27. And so 9 divided by 27 gives you 1/3. But again, we could use the laws of exponents here and recognize that we're dividing power to the same base. We keep the base, subtract the exponents. That'll give us 3 to the 1/3, or 3 to the negative 1. And so what this means, again, we've done this 2 different ways. We got 2 different answers, or 2 answers that look different, but they must be equal. So 3 to the negative 1 equals 1/3. So what we're seeing here, again, wouldn't have mattered if this was b squared over b to the 3. We would get b to the negative 1. And what this means is it's 1 over b. So when we have a negative in the exponent, we're going to flip the base and keep the positive exponent. That negative exponent, we flip the base, and then we have an exponent of 1. So here's some examples. Again, you can pause and go through these if you wish. So the answers here are there. I'll go over those just in case. Here I have 5 cubed, but on the bottom I have 5 cubed to the 4, so I'm going to keep the base, and I'm going to multiply those. That's 3 times 4 is 12. So now I'm dividing power to the same base, so I keep the base and I subtract those exponents. 3 subtract 12 is negative 9. And so now I see that I have a negative in my exponent, which tells me to flip the base and keep the positive exponent. In question B, the numerator here will be q to the 0 as I keep the base and multiply those exponents, divided by the denominator here of q to the negative 6. Now I can subtract, or I can keep the base and subtract these exponents. 0 subtract negative 6 is q to the 6, or it gives us q to the 6. That's one way of doing this. Another way is to look at this and say, okay, well, if you had q to the 3 to the 0, this is just 1. And so what we end up with here is 1 over q to the negative 6. Well, this negative sign tells me to flip the base. So really, what I'm doing is I'm moving this to the numerator, and that's where I have the q, and then I keep the positive exponent, so q to the 6. Okay, so you can do this either way you wanted to. This way is a little bit quicker, but this way might be less confusing. Now in question C, we have a base of x. We're dividing powers of the same base, so I'll keep the base of x, and I'll subtract these exponents. It'll be 2a plus b, subtract this exponent, so I'm going to put it in brackets. 3a minus b. And so that's going to give me x to the 2a minus 3a is negative a, and b subtract negative b is positive 2b. So what happens here is that I don't have to worry about this negative because I actually don't know what a and b are, and they could end up making that exponent a positive. So I'm just going to leave it like that. So now we'll evaluate these expressions. And evaluate means get the value of. So I want an answer here. So again, you can pause these and try this. Or pause this and try these, I guess it is, yeah. In any case, here are the answers. And again, I'll go over these quickly. Here we have 2 to the negative 4. Well, the negative sign tells me to flip the base and keep the positive exponent. Now, I don't care if you write it like that or you write it like this. Those are equivalent because 1 to the 4 is obviously 1. And so 2 to the 4 is going to be 16. In fact, it might be a good time to make a suggestion here in terms of what you need to have memorized. I think you should have the following exponents memorized. I think you have 2 squared, 2 to the 3, 2 to the 4, to the 5, to the 6, to the 7, to the 8, to the 9. 3 squared, 3 to the 3, 3 to the 4 is all you need to memorize with the 3's. 4 squared, 4 cubed is what you need to remember for the 4's. 5 squared, 5 cubed, 6 squared, and all the way down to, let's say, 15 squared. Those are the ones you need to know. I think you should memorize these. So I think you should know that, for instance, 2 to the 5 is 32. 2 to the 6 is 64. And I think you should know them like you know your name. I think you should know them how to go backwards, how to go forwards. And so I think that'll make your life a lot easier, because in this course I'm going to ask you to do things without a calculator. In fact, I think things will be done more easily without a calculator if you have these memorized. So, for instance, 4 cubed is 4 times 4 times 4. And so what we have here is 64. And 3 to the 4 means 3 times 3 times 3 times 3, which gives you 81. You don't need to know 6 cubed. All you need to know is that 6 squared is 36. You do have to know all the 10s. Like all of them, all the way up to 10 to the 100 or 10 to the 1000. Doesn't matter, because these are quite easy. 10 squared is just 1 and then 2 zeros, and 10 cubed is just 1 and 3 zeros. So you really should know all of those, and of course you should know all the ones, because 1 to the anything is just simply 1. So if we go back to our example here, I see that 2 to the 4 is one of the ones I should have memorized, and so that equals 16. And so 1 over 2 to the 4 is simply 1 over 16. In question B, I recognize that I have a negative in the exponent, so I'm going to flip the base and keep the positive exponent, and then 2 to the 4, the squared is 4, 3 squared is 9. In question C, I have a negative base and a negative exponent. Well, the negative exponent tells me something very particular. It tells me to flip the base and keep the positive exponent. 1 to the 2 is just 1. Negative 2 squared, that would be negative 2 times negative 2. That's going to give me positive 4. And now for question D, what we have here is a little bit of a trick question. In this case, the base is 3. And 3 to the 0 is 1, and the coefficient is a negative 1. So we have negative 1 times 1, which is negative 1. Had I asked what is negative 3 to the 0, the answer is 1, because anything to the 0 is 1. I didn't ask that in question D. So you have to be careful with that. I don't intend to trick you, but that can come up in other places. So here's some more examples. In fact, I think this first one was one we just did. Question B is 1 over 5 to the negative 3. So the negative tells me to flip the base, and then I know what 5 cubed is. It's 125. Question C, I have this addition here. And so that's going to be fairly difficult for us to evaluate with this exponent. If you recall, I can't just have my power of a power here for the same reason that x plus 4 all squared is not x squared plus 16. We have to expand the binomial. We have to FOIL that out. So what happens here is that we have to follow BEDMAS, and since we can evaluate what's inside the brackets, we should do that first. So you can see here that 1/2 to the negative 2, flip the base because of this negative exponent, and that'll be 2 squared, which is 4. 7 to the 0 is 1, so I have 5 to the negative 2. Flip the base, keep the positive exponent, that's 1 over 25. And I have a similar scenario here, 2 to the negative 1 plus 6 to the negative 1, then all to the negative 2. I'm not going to worry about that negative 2 exponent until I evaluate what's inside the brackets. And 2 to the negative 1 is 1/2, and 6 to the negative 1 is 1/6. And so I simplify those by getting common denominators here. I see that I can write 1/2 as 3 over 6, and 3 over 6 plus 1 over 6 is 4 over 6, which reduces to 2/3. And now I can flip the base and keep the positive exponents. Had you not reduced this, you could have flipped the base here and kept the positive exponent, and you would have given me 36 over 16. And that would be an acceptable answer for me as well. So what we can do now is we can start to solve some exponential equations, but in order to do that, we're going to have to have common bases. So we'll take a moment here and practice getting some common bases just by simplifying an expression. So here you see I have 4 to the 3x times 8 to the x over 16 to the negative 2. Well, all of these can be written as base 2. And so 4 is 2 squared, 8 is 2 to the 3, 16 is 2 to the 4. So I'm going to rewrite those there. That doesn't look like simplifying, but what I notice here is I have a bunch of powers of powers. So I'm going to keep the base and multiply those exponents. 2 times 3x is 6x. This one here, I'm going to keep the base and multiply those exponents. Keep the base, multiply those exponents. Same thing on the denominator, keep the base, multiply those exponents. Okay, so now you can see that, yeah, okay, it does kind of look like we're simplifying this. The numerator is multiplying powers the same base, so I keep the base and add those exponents. Now all I have is division of powers of the same base, so I keep the base and subtract those exponents. And what I see here is that now I've been able to write this as a single power. I took this expression here and I rewrote it. It equals this, and that is powerful because, again, most of math is being able to write something differently to make it more useful. So here's one that's asking you to evaluate this without a calculator. So if you want to give that a go, you can. I'll do that out. What I see here is the bases are 27, 81, 9, and 1/3. Now I certainly don't know what 81 to the -5 is. I'm not supposed to either. I'm not supposed to know what 3 to the 7 is, or 27 squared. But I do know that all of those bases are powers of 3. So I'm going to rewrite the 27, the 81, the 9, and the 1/3 as powers of 3's. Now, in each case, I have a power of a power. So I'm going to keep the base and multiply those exponents. And so what I have here is keep the base of 3 and multiply 3 times 2. That gives me 3 to the 6. Multiply 4 times -5. -20 is the exponent. Again, the base is still 3. Same thing down here. Base of 3, exponent of -8. Base of 3, exponent of -7. Now what I'm doing is I'm multiplying the powers of the same base. So the numerator here is going to be 3 to the 6 minus 20, or 6 plus -20. And same thing with the denominator. It's 3 to the -8 plus -7. And that's going to give me -15 as the exponent. Now I'm dividing powers of the same base, so I keep the base and subtract those exponents, and I get the answer 3. So if you're down at the pub or something and you want to impress somebody, you could write that out and say, hey, you know what this equals? I can do this in my head. This equals 3. I'm sure that will impress them. Or maybe not. Anyways, so now we can solve exponential equations. Whoops. We can do this if the bases are equal, because if the bases are equal, then the exponents have to be equal. And so the question now becomes solve for x, or find the roots of the equation. And here, the equation what we have. I know this is an exponential equation because the unknown is in the exponent. And so what I have to do for now is I have to be able to find common bases, and I see that a 9 minus 27 can be written as base 3. So 9 is 3 squared, 27 is 3 to the 3. Again, I have powers of powers, so I can keep the base and multiply the exponents. When I multiply these exponents, it's 2 times all of this. And so that gives me 3 to the 4x minus 8 equals 3 to the 12. Now, since my bases are the same, as we said right up here, my bases are the same, then my exponents have to be the same. So I can write a new statement, and I can just simply say that 4x minus 8 has to equal 12. In order for these two expressions to be equal, everything's got to line up. The bases are already equal. That means that the exponents have to be equal. And so I'm actually writing a new statement here. So we would technically put like a therefore, you know, if this is true down here, then therefore 4x minus 8 has to equal 12. I add 8 to both sides, divide both sides by 4, and I get x equals 5. So now if I plug in 5 back here, I would have the exact same value on each side of the equation. So here's one. It looks a little nasty. My strategy is to first recognize that the unknown is in the exponents. So I'm able to do this as if I can get common bases. And I see the bases are 64, 8, and 128. And I recognize those as base 2. 64 is 2 to the 6, 8 is 2 to the 3, and 128 is 2 to the 7. And here I have 1 over 128, so I want to flip that, which means I'm going to put the negative in the exponent. Of course, now what I have is the power of a power. So I'm going to keep the base and multiply those exponents. Now I have multiplying powers of the same base. So I'm going to keep the base and add those exponents. And then, of course, what I have here is 2 powers. It's important that you have to have 2 powers here. You can't have anything else. Notice that I didn't say if the bases were the same, then the exponents are the same in this step, because I didn't have the left-hand side simplified. Now I have 1 power equals another power here, so if the bases are the same, then the exponents have to be the same, and therefore, it's a terrible therefore sign, but therefore 30x has to equal negative 7. I divide both sides by 30, and I get x equals negative 7 over 30. And just leave that. Don't use a calculator to do that. I don't care what the answer is. What I have to care about as your instructor is I have to give you, right now anyways, I have to give you an expression that has the ability to get a common base. So I don't care how nasty the answer ends up with, or ends up being. I just have to tell you that you can get common bases. And so here's one, same kind of question. Find the roots of the equation below. 3/8 to the x minus 48 equals 0. This doesn't actually look like I can get common bases. And I can never multiply the 3 and the 8 together. I don't have 8 there. I have 8 to the x. And since I don't know what x is, I don't know what 8 to the x is. And so I can't multiply that by 3. So what I have to do here is instead I have to what I call isolate the power. And so I'll say isolate the power each and every hour. This is what the hippies used to say back in the 60s. You know, they were doing these problems. Everybody thought that they were having sit-ins to, you know, oppose the government and stuff and stick it to the man, but they were actually just doing these problems. I'm sure of it. So I'm going to isolate the power. The power is 8 to the x, and by the way, those jokes kill when it's face-to-face. I don't know how they're coming off online, but they're hilarious, I'm sure. Anyways, I'm trying to isolate the power, so I'm going to undo what's being done. I'm going to simply add 48 to both sides, and I'm going to divide both sides by 3. And look, now I can get a common base of 2. So what I see here is that 8 is 2 to the 3, and that was 2 to the x. So this is 2 to the 3x, and 16 is 2 to the 4. Since my bases are the same, my exponents have to be the same, and I solve for x. So here's some that you can try. I'll give you, or you can pause here and take a moment. But I'll go over each of these. In question A, I have to isolate the power. Again, what I see here is the power is the base of the exponent. So I'm going to subtract 7 from both sides. Now I can get common bases. 64 is 2 to the 6. Since my bases are the same, my exponents are the same. Now I'll subtract 2 from both sides and divide both sides by 2. Question B is fairly similar. I could divide everything by 4. But what I notice here right away actually is that I have bases of 2. So I have 2 squared times 2 to the x plus 3, and that's going to equal 2 to the 8. So here on the left hand side I now have the multiplication of powers to the same base. So I'm going to keep the base of 2 and add those exponents. Now since I should say first I have 2 powers that are equal, I know that if their bases are the same, then their exponents have to be the same. And then I simply subtract 5 from both sides. Question C, 4 to the x minus 2 equals 8 to the 4. I don't know what 8 to the 4 is. I don't really care about that. I know that I can get common bases of 2 here. And in each case I have a power of power, so I keep the base and multiply those exponents. Now I have 2 equivalent powers. Okay, they have the same base, so their exponents have to be equal. Now I'm just adding 4 to both sides and then dividing both sides by 2. In question D, this is a throwback question because it's not an exponential equation. What happens here is that the exponent is not where the unknown is. This is simply quadratic. And I can solve this by using the quadratic root formula since one side equals 0, or I can factor it, as you see here. I needed two numbers to multiply to give me -10, and two numbers to add to give me -3. And so what we have here is x minus 5 and x plus 2, since the numbers were -5 and plus 2. And now I can solve, and I see that x equals 5 or x equals 2. So on your final, you will have a question that says, find the roots of the following equations. Some of them will be quadratic, some of them will be linear equations, some of them will be exponential equations. And you have to know which one's which and how to tackle it appropriately. So we'll now take a look at some patterns here, geometric patterns. But first, let's recap what we've seen with the linear patterns. First of all, we knew that the common difference is on D1, and that means we could write the equation in terms of, or the pattern in terms of these equations. Then we saw we had quadratic patterns where the common difference is on D2, and we could write those patterns with the following equations. But if we had an equation like this, or sorry, a pattern like this, 3, 6, 12, 24, 48, well, if you go to try and find a common difference, you'll get the exact same values that you had inside your pattern. But of course, just because there's no common difference doesn't mean there's not a pattern. What we see here is that there's a common ratio. We can divide these out and get a common ratio, and that means that this is called a geometric pattern. Here's what we have here. So instead of subtracting, we're dividing. 6 divided by, I'm trying to make a dot there. 6 divided by 3 is 2, 12 divided by 6 is 2. So the nice thing about geometric patterns is that the common ratio shows up right away, or it's not a geometric pattern. Not like a quadratic where you have to find D1 then find D2. What we have here is very straightforward. It either shows up or it doesn't. And since it does show up here, I can rewrite this equation, or this pattern, like this. I can write it as the first term is 3, then the second term is 6, but I can write that as 3 times 2. The next term is 12. I can write that as 3 times 2 times 2. And of course that pattern continues. So I could also write this pattern as 3 times 2 to the 0, 3 times 2 to the 1, 3 times 2 to the 2. And what you'll see here, especially if we remember that 2 to the 0 is 1, what we see here is that when n equals 1, the exponent is 0. When n equals 2, the exponent is 1. When n equals 3, the exponent is 2. And so we can quickly get a pattern here. We can now see that I can represent this as any of these values. So Tn equals 3 times 2 to the n minus 1, where 3 is the first term and 2 is the common ratio. So if we check to see if n equals 4, and to find the fourth term, I should get 1, 2, 3, 4. I should get this 24 here. And of course we have to follow the order of operations. I have 2 to the 4 minus 3. Well, 4 minus 3 is 1. It's implied that the exponent's in brackets there. 2 to the 3 is 8. 8 times 3 is 24. Notice that the common ratio is 2, and that's always going to be the base. Common ratio is always the base of the exponent. And the first term there is the coefficient. Oops. So if we have this pattern, 5, 10, 20, 40, 80, what we see here is that we can represent this as the equation Tn equals T1 times R to the n minus 1, because the common ratio, the common ratio is a 5, or common ratio is a 2. So we divide these. And there's our base, and the first term is a 5. That's what we have here. And again, we can check this by plugging in n equals 5, and we get the correct answer. So here's an opportunity for you to find the 10th term in each of the patterns. So again, I'll go over these, and you can pause this now and try these if you wish. So the first example, we have a common ratio of 1/2, 50 divided by 100, and the first term's 100. So there's our equation. We can plug in n equals 10, and we can solve this out. And this is useful to use your calculator. And I just kept as many decimals as possible. The next one, we have a common ratio again of 4, and the first term is actually 1/4, about 0.25. And so I can again plug in n equals 10 and solve. Question C, I do not have a common ratio, but there's a common difference. This is a linear function, so I have to use a completely different equation here. And I get the 10th term to be 32. And the next one, I have find the common ratio here. I have -2 divided by 1 is -2. 4 divided by -2 is -2. -8 divided by 4 is -2, etc., etc. And so what we see here for the first time is that we have a common ratio of -2. You can see that the common ratio is negative because the term values are flipping from positive to negative. And so what we have here is the 10th term of -512. When you have a negative base, like we did in this case, and the exponent is an odd number, then it's going to be a negative value. But when the exponent is a positive, because you'll have a negative times a negative, an even number in bounds. Sorry, I think it's a positive there. When the exponent is an even number, the value that we'll have is going to be a positive value. Oh no, shoot, I messed this up. That's just -128, not 1/4, and this is simply going to be 64. I was thinking if the exponent was negative, then it'd be a 1/. Flip the base and keep the positive exponent. Alright, so for which term has a value of 768 in the following pattern? And so again, we can see quickly that there's a common ratio here of 2, and the first term's a 6. So now we want to plug this in for our Tn value. So I'm going to isolate the power by dividing by 6. Now I can get a common base. Since my bases are the same, my exponents are the same, and so my 8th term in this pattern would be 768. So now we can get to word problems because we understand these patterns. So if I look at an exponential growth of a bacteria, let's say it doubles every 6 hours. Well, if I start with 1 bacteria, in 6 hours I'll have 2. And then those would have doubled, so I'll have 4, and then those would have doubled, so I'll have 8. And what we can do is we can put this into a table here. Instead of n, I can have the number of hours since the experiment began. And that means 0 hours is when the experiment started, and I started with 1 bacteria. And 6 hours later, I had 2. And so what I can see here is that there's a common ratio, but the n values, I really shouldn't be calling those n values, they actually don't increase by 1, and they don't start with the first. They start with 0. And so we have to find a new equation. Right? We can't use this equation here. This Tn equals T1 times R to the n minus 1. So we're going to have to come up with a new one. This still works this equation still works if you have the first term, you have, the term, I'll say it differently, the term when n equals 1, and your n values go up by 1. But here's that's not the case. So what we see here is that we need to have use this equation. Y equals A naught, which is still your initial amount, times the common ratio to x over the period. And what that means is the period is when the x, or by what the x values increase by. So they're increasing by 6 here, and that will be the period. Because what we see here is it's doubled, so we need this exponent to be a 1, because the common ratio will be a 2, but it's got to be a 1 when x equals 6. So 6 divided by 6 would give me 1. And when it quadruples, we would like this exponent, we need this exponent to be a 2. So the exponent has to equal 2, and that's when x equals 12. Well, again, if we divide that by 6, we'll get our 2. And so we see here that our function is y equals 1, our starting value, times 2 to the x over 6. So if we take that question, that situation, we can ask ourselves how many bacteria are present after 50 hours. So just by reading this, I don't even need to do the table, I see that it doubles every 6 hours. Well, every time it says every, that's the period. So the equation we just had works. I'm going to plug in x equals 50. I'm going to use my calculator. I'm going to solve this. Again, make sure you're doing the exponent first, or you at least put it in brackets. 2 exponent. You're either looking for that button, which is the caret, or you're looking for x to the y or y to the x, something to that effect. Then you're going to go bracket 50 divided by 6. So we can also solve for when there will be 128 bacteria present. I'm going to plug that in for y. I'm going to take common bases. Since my bases are the same, my exponents are the same, and so in 42 hours there'd be 128 bacteria. So exponential growth is very powerful. We'll talk more about that later on. But it's also pretty easy. From the word problems, even though I don't give you the equation, we can very quickly get that equation, like within seconds. So we'll do more of that next week.